Hey guys, so today we're going to go over old lectures from my Foundations 2 class, and we're going to start with our first topic we covered in the class, asymptomatic behavior of functions. So we're going to go over big O, big omega, and big theta notation. So what we'll learn, big O, upper bound growth rate, big omega, lower bound growth rate, and big theta, which is the bounding of the function. So as a basic growth hierarchy, we start with log, polynomial, and exponential growth in that order of growth hierarchy. Big O. So if f of n is omega or big O of g of n, there exists constants c and k such that f of n is less than c g of n for all n and k. So big O gives us an upper bound of how a function grows. So it means that the first function can be no faster, but it can be the same growth towards infinity of g of n. So, for example, 3n to the power of 4 grows less in infinity if n is going to infinity than n to the fifth power. Same goes with the rest of the function shown at the bottom. Understanding big O visually. So, if n is a person walking and big O says no matter what, you'll never hit your head on g of n, it's essentially a ceiling. G of n is a ceiling. Big omega. So it's essentially the opposite. F of n is greater than C G of n for all n and k. So this gives us a lower bound. F grows at least as fast as G. Key relationship, pretty much the inverse of what we just showed. Big theta. So F of n is theta G of n if there exists constants C1 and C2 that can bound C2 and C1 G of n, F of n for all n and k. So F of n is sandwiched between two multiples of G of n that bound uh, f of n towards infinity. So uh, omega and theta are upper and lower, and then big O is upper. Growth hierarchy, slowest to fastest, logarithmic, polynomial, exponential. These are some examples. Just look at the dominant terms. And then these are the useful formulas. So, cool beans. Key takeaways, big O, upper bound, big omega, lower bound, big theta, tight bound,